Hello everyone, welcome to this fifth lecture on radiative heat exchange. Today we will look at some practical aspects related to heat exchange. The first one is view factors, which we introduced in the last lecture, but we will look at the details of today. And the second topic is on adiabatic surfaces, which is a special case of a multi-surface problem, which we can apply to many practical situations. Sources for today is chapter 3.10, where the view factors are discussed, and 3.12, where the adiabatic surfaces are discussed. Note that we are skipping over 3.11. Chapter 3.11 is the chapter where this general surface has been introduced that we talked about in the first lecture and in many of the subsequent lectures. We will also look at that specific figure today. So we'll start with the view factors. And last time we were calculating the heat transfer rate between two surfaces that we denoted 1 and 2. And the heat transfer rate, so how many watts is being transferred, so joules per second, we expressed as this Q dot and then 1 to 2, signifying that this is the heat transfer from surface 1 to surface 2. We showed that this is dependent upon the area of your surface. Then we had this symbol F12, which is the view factor, which we will come back to. And finally, we have this EB1, which is the black body emission from that specific surface, or from a black body that has the same temperature as that surface. So the view factor F12 is defined as 1 over area 1, and then please note the indices here. The first index in the view factor corresponds to the index of the area that we have divided with in front of the integral. And then we have a double integral over area 1 and area 2. So that's the two areas that go into the view factor. And then we have some geometrical relations that were introduced last time. So the view factor, F12, symbolizes the fraction of A1's field of view, which is covered by A2. So you could also imagine this as how much of A1 is seen from A2, if you want. So how much, it's a fraction of A1's field of view, which is covered by A2. We'll see some examples shortly, and then hopefully you'll have an intuition to what it means in terms of numbers. Correspondingly, if we look at the opposed heat transfer rate, Q21, that will be defined as A2, so the area from which this radiation is originating, which is why then we are looking at EB2, which is then the black body radiation from a surface that has the same temperature as the surface in question. And then we have F21 for the view factor. F21 is defined in the same way. It's then 1 over area 2, because 2 is the first index. And then we have the same integral here, except that the order has been switched, but that doesn't change the value of the integral. Then it is important to note that we developed these relations based on ideal or semi-ideal formulation. That means that our surfaces are black or gray that reflect diffusively. So this essentially means that we have a constant emissivity and a constant absorptivity for the surface. But this is a good approximation for many surfaces that are of practical importance. Last time, we also observed that the two integrals, if you change the order of integration, you get the same value. I already mentioned this as well. That means that if we multiply the view factor Fij with the corresponding area Ai, that should be equal to Aj multiplied with Fji. And if you remember, this Fji would then be 1 over Aj times this double integral, while the Fij equals 1 over Ai times the double integral. Sorry. So if we multiply this with the corresponding area, we of course get this relation that we have here. This relation between areas and view factors is known as the reciprocity relation, or the reciprocal relation. And this is very useful because it allows us to determine view factors in a system where we know the other one. So if you know one view factor and the corresponding areas, you can easily calculate what the other view factor is. It also allows you to do some simple substitutions in the expressions that we will look at towards the end of this lecture and the next lecture, making the math come out more convenient. So that was the reciprocity relation, or the reciprocal relation. Another very important relation that we will use a lot is the so-called enclosure rule. That's also known as the summation rule. This one is valid for enclosures, hence the name. That means that you need to have a geometry like this, where you have well-defined surfaces around your whole system. If you have such a system, the sum of all the view factors, if you sum over all the j's, you get 1. So note that we are not summing over I in this sum, we're summing over all the j's. Up to n, where n is the n surfaces that we have surrounding our system. So this summation rule is applied to any of the n surfaces in an enclosure. And it follows from energy conservation. All radiation which is leaving some surface I has to be intercepted by the enclosing surfaces. If not, energy will be lost within the system. Another interpretation of the view factor, Fij, is that it represents the fraction of radiation leaving I intercepted by J. This is equivalent to our first the definition that we introduced already. Going back, sorry, it's the fraction of A1's field of view, which is covered by A2. So So necessarily if a part of the field of view of A1 is covered by A2, that part will necessarily then also intercept any radiation or light waves, if you want, that come from the first surface. So an important or interesting point in that respect is that we, from the enclosure rule, we get a term of the type FII, which is self-interception. We could imagine it if we have a system of 3 surfaces. So we will have, let's say, 1, 2, 3, and we do the enclosure rule, J equals to 1 to n of Fij. This should equal to 1. I can be any one of these surfaces, but let's choose surface number 1 for the sake of this example. So then we would do the sum of j equals 1 to n of f1j equals to 1. And that tells us that f11 plus f12 plus f13 equals to 1. So, as I said, we get a term FII, or F11, for this example, which represents self-interception. If the surface I is concave, then FII is greater than 0. Concave surface means a surface, which is not like this, but like this. Why does this give a view factor of itself which is greater than 0? Well, it is because the surface sees itself. You can imagine a ray coming from here will hit the surface itself, a ray coming from here will maybe hit there, etc. The surface is able to see itself. If the surface is convex or flat, then this self-view factor is 0. A convex surface would look like this, and then we would have the surroundings. And then obviously this one will not reflect upon itself. Neither will a flat surface as we have in this sketch. So in that case, the self-interception or factor, or the view factor with identical indices, equals to 0. So that gives us some additional information that we in principle then can use to determine F12 and F13 if we need to do so. So we'll move on to talk about some practical calculations related to view factors. And if we have a enclosure with n surfaces, then we need to calculate n to the power 2 view factors. However, or thankfully, we don't have to calculate all of them, because we can determine n view factors from the n enclosure rules. Furthermore, we can determine n times n minus 1 divided by 2 from the corresponding n times n minus 1 divided by 2 reciprocal relations. So that means, accordingly, that you started with n to the power 2 view factors that you had to determine. Then you determined n of these from the enclosure rules, and you can also compute n times n minus 1 divided by 2 from the reciprocal relations. And in sum, this gives you 1/2 times n minus 1 view factors that you have to determine explicitly. That can be either by calculating the actual integral that you need, that you can do in principle at least, or you can determine it from a relation stating that, for example, this is a flat surface, so f11 is 0, for example. So we'll look at some examples now before we go on to the adiabatic surfaces. Let us first consider a system which has two surfaces that form an enclosure. This can, for the sake of example, be two concentric spheres or two long cylinders. It wouldn't change our results. And by long, I mean infinitely long. But of course, for the concentric spheres, it's true for all kinds of spheres. So if we have two surfaces, then we have n to the power 2 equals 4 view factors, which are needed. And these 4 are then f11, and then we have a corresponding f22. So how much of these systems see themselves. And then we have f12 and f21, which are the opposing view factors, so to speak. However, fortunately, only one single view factor needs to be determined explicitly, because 2 times 2 minus 1, that equals 2, divided by 2 equals 1. So you only need to do one of the view factors, and the rest of them you can find from the corresponding relations. So the system that we are interested in looks like this. So this is either a sphere, so this could be a sphere within a sphere, or it can be two infinitely long cylinders. Doesn't change the results. Surface 1 is the inner one. It was a bad color, sorry. And surface 2 is the outer one. And what we are, of course, interested in calculating is whatever heat transfer rate we have between these two surfaces. So we're not going to consider whatever surface 2 is emitting to the surroundings. Okay, that's why we only look at these view factors. So the easiest way to determine all of the view factors here is to note that f12 equals to 1. You can calculate that explicitly by doing the integral if you want, or you can simply see that all rays being emitted from surface number 1 will be intercepted by surface number 2. So 100% of the field of view of surface 1 is covered by surface 2. So that's why f12 has to be equal to 1. Next, we look at the or we can also look at the reciprocal relation. That one states that, well, we're going to sum Fij and that should equal to 1 for all j's. Now if we choose I equal to 1, then we have f11 plus f12 equal to 1. And since we already know that f12 equals to 1, then we get that f11 equals to 0. This could have also been deduced from the fact that surface number 1 is convex. So it doesn't see itself. So now that we know the value of the view factors that have a 1 as the first index, we can use the reciprocal relation to calculate one of the view factors that has a 2 as the first index. So the reciprocal relation tells us that A1 times F12 equals to A2 times F21. This follows from the equality of these double integrals that we studied in the last lecture. So since we now know everything here except F21, at least in principle, then we could calculate F21 as the ratio of A1 over A2, and in reality this one should be multiplied with F12 of course, but F12 equals to 1 already, so we only get A1 over A2, ratio of the areas. Then again we can use the enclosure rule to say that F22, F plus F21, again equals to 1. And since we already know then the F21, we can from that calculate F22 as 1 minus A1 over A2. So again we remember that this F22, that represents the self view factor, and of course if surface number 1 had not been present, then A1 would be 0, and then F22 would be 1, because it is the inner side of a circle or a sphere, and it will see its entirety, the entirety of its inside. However, now that we have a surface with a non-zero area on the interior, this will block some of its field of view, and that's why we get the value which is expressed like this. We'll move on with an additional example, somewhat simpler perhaps, where surface number 1 is a flat wall like this, and surface number 2 is a half circle or a hemisphere, depending if you do it in 2D or 3D. Now again, surface number 1 is flat. So since it is flat, it will not have a self view factor, i.e. F11 is equal to 0. And we solve it the other way around. We now use the reciprocal relation again, F11 plus F12 equals to 1, and that gives us that F12 equals to 1 again. And this is again because all of the radiation leaving surface number 1 will be intercepted by surface number 2. Similarly, we go back to the reciprocal relation in order to determine F21. Again, this is given by the ratio of the areas. Again, this should have been multiplied with F12, but F12 is equal to unity, so we skip it. And this again gives us the same value for F22. One minus the ratio of the areas. So this one is actually the first system we looked at, where we had a cylinder within a cylinder or a sphere within a sphere. Another example, here we have again our flat surface, but now we have separated our hemisphere or cylinder into 3 different parts. Surface number 1 is still flat, evidently. So that means that F11 is still 0. But if we now try to use the enclosure rule, this will essentially then be F11 plus F12 plus F13 plus F14, because we have 4 surfaces. This should be equal to 1. And then we see that the algebra becomes slightly more tedious, because we'll need much more relations to solve this. The final example I would like to highlight is the following. We have a circle here that we denote 1, and we have a infinitely large surface down here that we denote 2. Now, if we start to look at this, we will note that F11, the self-view factor, is equal to 0 necessarily. And that is because this sphere or circle does not see itself. So no of its radiation will be intercepted by itself. Excuse me. What can we then say about F12? Well, I leave a question mark for now, but I can already spoil that it's not equal to 1. Same if we go for F22. Well, F22 is also is flat, so that has a self-view factor of 0. And again, what is F21? That's not equal to 1 either. That's simply because neither of these geometries block the full view of field of view from the other one. So as I said, we do not get F12 equals F21 equals to 1. And the reason for that is that we do not have an enclosure. So there's no enclosure in this system. We are missing sort of the information of whatever these imaginary surrounding walls are. So with the absence of these, we cannot use the enclosure rule. So we'll have to do something else. If we go back to the definition, Fij represents the fraction of radiation emitted by I intercepted by J. So if we look at surface number 1 again, and we draw a line through its center, we see that the rays that are leaving below the center line, they will in principle hit surface number 2 at some point. While the rays that are exactly here on the center line, they will continue parallel to this surface towards infinity, while the ones above will essentially, or will never reach surface number 2 at all. So This means that around, or not around, but all the radiation, or half the radiation actually, emitted by the orange surface number 1 will be intercepted by surface number 2. So F12 equals 1/2. Since the rear half of surface 1 radiates in the wrong direction. Now that we know F12, we can use the reciprocal relation to calculate F21. And F21 is then equal to F12 times A1 over A2. And this one is actually equal to 0, or approximately equal to 0, since area 2 tends towards infinity. Infinitely large plate will not be bothered by a small circular thing present above it. So hopefully this helps your intuition. There are many examples in the literature, and there has been there is a compilation online that a good friend of mine, Andre from Canada, sent to me. It's thermal radiation .net. So we'll have a brief look at that. Go then to thermalradiation.net. So we get to this web page, and on the top here we have configuration factors. So I clicked on configurations factors, and then here on the right hand side there is a table of contents where you have a lot of different view factors. For instance, here in section C, third column, you can go to, for instance, cylinder 2, and then you will have a cylinder 2, for example, so a concentric cylinder of infinite length. And then you get the exact relations that we just derived. If you click next, you can get another one, exterior of infinitely long cylinder to interior of concentric semi-cylinder. Go back to the table of content, planes and rectangles, for example. Let's see, we can have two infinitely long plates in a wedge. So here we have that system where we have F12 and F21. So this is an extremely useful reference for those of you working in radiation. Particular interest is this one called Other, where we have the very useful relations for a view factor for a standing pig to various rectangles. So thanks to Andre for sending me this link, to contributing to the content all the way from Canada. Next topic for this lecture is an introduction to adiabatic surfaces. So again, we will return to this starting point that we showed in the first lecture, where we define all of the incoming and outgoing fluxes to our general surface. And what we were or have been discussing is this net heat flow. And what we're aiming to do now is to put this single surface into a multi-surface setting. So how will this behave in a system, for example, an enclosure of multiple surfaces? So we'll start with a few definitions. And as I just said, the net heat flow from surface I, Qi net, is the area multiplied with the difference in flux. So the flux here, the outgoing flux, is the radiosity here, while the incoming flux is the irradiation, Gi. So what we want to do here is to see or change this expression. We can note that the irradiance, Gi, actually goes into the radiosity itself. So we're going from this one to this one. What we have is that the radiosity equals rho Gi, rho I Gi, plus epsilon I E B I. Refer back to this figure. The radiosity equals to the emitted radiation plus rho I Gi, which is the reflected external radiation. So the radiosity itself depends upon this G, the irradiance. So what we can do here is that we can substitute this G with this one, and we get this expression instead, which then depends upon the radiosity and the black body emitted radiation. We will now introduce some notation, let's see, where we introduce then that the reflectivity, rho I, equals to 1 minus epsilon. So that allows us to replace this one. And if you then do some manipulation of this expression, you end up with the following thing. Qi net, so the net heat transfer from your surface, equals the black body emitted radiation. So you see we have a minus and a minus, so it comes out as a plus, minus the radiosity divided by this thing, which is the reflectivity divided by the surface area multiplied with the emissivity. You should check this for yourself. And this term, rho I over AI epsilon I, we call it capital Ri. And this is interpreted as a surface resistance. So resistance towards heat transfer equivalent to the resistances to heat transfer you've seen in convection and conduction problems previously. So depending upon the magnitude of EBI and JI, or JI and GI, the surface can act as both a source and a sink to radiation. So if JI is greater than GI, so let's return to our figure. If JI is greater than GI, that means more is leaving than entering. This can only be possible if we have a positive heat flow to the surface. So this is a source of radiation to the system. The opposite, if Ji is smaller than Gi, then we have a sink for radiation. So this would typically be your cold environment, and this may be a hot metal surface, for example, generating a lot of radiation, which is then lost to the environment. Now a particular case is that of a adiabatic surface. The adiabatic surface has the property that the total emitted energy per time, AIJI, contains as much energy, again per time, as that which is absorbed, AIGI. That results in a net heat transfer equal to 0. Note some terminology. It is the surface AI which is described as being adiabatic. And this is adiabatic because it has a net heat flow equal to 0. Since these surfaces will be of particular practical interest in the calculations, we will denote them with the notation R, subscript R, and that is for refractory. So the definition here is that for adiabatic surfaces, AR, we have QR net equals to 0. Net heat transfer is equal to 0. And that also means that the outgoing flux is equal to the incoming flux. Now if we go back to equation star, the equation star was this one, which you have to derive for yourself. So if we go back to this one and we introduce that the net heat transfer rate is 0 for an adiabatic surface, we get that the radiosity of an adiabatic surface equals to EBR, which is the blackbody emitted flux, or the emitted blackbody flux. It's still equal to GR as well. So that gives us the interesting relation that the radiosity equals to the incoming radiation equals to the blackbody radiative flux. So this expression tells us that a adiabatic surface, AR, has an overall radiation, JR, which is emitted, which is then again equal to epsilon R EBR plus rho R GR. This in total corresponds to EBR from a hypothetical black surface with the same temperature. That is, it behaves as though rho R is 0 and epsilon R equals to 1. And yes, this is a black surface. So the adiabatic surface behaves as though it were black, even though it in reality is gray. So the adiabatic surface, since it does not absorb or doesn't absorb any net radiation, it has a 0 net net heat flow, it will rapidly attain a equilibrium temperature, which we call TR, which depends upon the temperatures depending upon the temperatures of the other surfaces in the system. And the reason for that is that, well, EBR, which is the black body or the emitted black body flux, equals to sigma TR to the power 4. This is just Stefan Boltzmann's law. And from our relation, this equals to GR, actually, which is the incoming irradiation. So everything becomes quite tightly coupled in this situation. So in the next lecture, we will put this into practice. So we'll see how we can describe and compute systems with multiple surfaces. Have a nice week, and catch you next time.